This video discusses inverse functions, and more specifically the calculus part of this, the derivative of an inverse function. Inverse functions, you possibly should have seen somewhere in algebra or pre-cal or something like that. We don't go into the trig inverse functions in this section. That's dealt with at a later section, which sometimes could be in Cal 1 or Cal 2, just depends on how the course is set up. As of the making of this video, it's a Cal 2, but that could change, so don't mark that down in stone. But anyway, notation, -1, -1 I never have liked that because it looks like it's an exponent, but well, we have to kind of live with it here. I would have thought like a capital I or something would have been neat there, not lowercase I for imaginary, but I guess I wasn't around several hundred years ago to come up with this. So, and inverse functions have this behavior that when you do them composite, f of f inverse or f inverse of f, you get x as the response. That's how you know they're inverse functions. And you see Stewie's mentioning over here that that's not an exponent, so it's not 1 over that function. Now, without going into this, here's a lot of the algebra stuff that I'm not going to really test you on directly, but you could obviously go back and if you want to read up more on inverses, you could. But one thing about inverse functions, essentially every point on the graph versus inverse, you're just reversing the x and the y coordinates. Okay. See how those flip? And then a function must be what's called 1-to-1 for the inverse to exist. Essentially, 1-to-1 means you can only have one x per each y, unlike a regular function, like this one for x squared. Let's say if you put -2 in there for x, you'll get 4. If you put +2 in there, you'll get 4. That's okay for a regular function. A regular function just can't have one x producing more than one y, but it could have different x's mapping to the same y. For 1-to-1, that's not true at all. It has to be directly. You can't have two x's merging into one y. So sometimes with functions like this, the way they can get around it, which is that's how it's done when you do learn about trig inverse functions, is they do it like this. They pick a certain section of the graph. Like this one, if I pick just the right half of the parabola, I'm okay, because it wouldn't have the matching y's. And this is saying, of course, to be a function, you have to pass both the vertical line test and the horizontal line test. So here, the function then must pass both the vertical line test and the horizontal line test to be 1-to-1 and have an inverse. So you see, even though that, obviously this is a function, f of x equals x squared, it's fine on the vertical line test, no problem, but it fails the horizontal line test. But this one's okay. You can't cross it twice, either vertically or horizontally. So, good shape. Finding an inverse function. This is how this is done algebraically, but this is not going to be the primary focus of this section. Let me mention this idea as a review of inverse functions also. A function and its inverse, they will be a reflection across the line y equals x. If you flip it over across the line y equals x with a function and its inverse, and that's what's happening here. So it reflects that way. But technically, the algebraic process for finding the inverse function, we would switch the x and the y and then solve for the new y. So you see f of x, of course, is y. So you replace that y with x, this x with y, do a little algebra to it, +1 both sides, and then take the cube root of both sides. So when you solve for this new y right here after you take the cube root, that y will be f inverse of x. So then it's the cube root of x +1. Now, a lot of times a function, the algebra would be either impossible or virtually impossible, whatever the case may be. A nightmare would be accurate trying to solve for it. Here's a good example of that. But anyway, see, so let's suppose we wanted to find what the derivative of the inverse function is. In other words, we want to find the tangent slope, rate of change, all the stuff that derivative gives you at a particular point. Well, for this example we just did, that would, we found the inverse function. So all we would have to do is take then the derivative of this cube root of x plus 1 and then plug in our x. And that's all fine and dandy. However, what if the function is not really invertible algebraically? Now, there's a way to verify whether or not a function is one-to-one. I'm not going to worry about having you do that. That's not important. You can just assume that the function that you're given is one-to-one. You don't have to worry about it or verify it or anything. So like I told you right there, or just even if I didn't put that there, you just can assume it's one-to-one. So from the last problem, this is the graphs from up here. So you see I typed in the original y equals x cubed minus 1, and then y equals x, and then y equals the cube root of x plus 1. The y equals x is in there to show what I showed right here, how it reflects. And let me zoom in on this a little bit. All right. So you see that on the line y equals x, notice these two graphs, how if you flip one of them across the other y equals x line, they'll be the same graph. They're perfectly symmetric about that y equals x line. So well, anyway, back to this function. We can't see, so if you're going to try to solve this algebraically and then take the derivative, that's not going to work, because you're not really going to be able to solve that for y no matter how hard you try. So we can't do it. However, we can still get the derivative of the inverse function without technically knowing the algebra of the inverse function. So this is a neat little trick. So like say here, suppose we want to find the inverse function derivative at some value such as 9. Let's see how we do that. Now, it's not that complicated. Students will still have trouble with this. It's a very straightforward process, but I don't know why it seems to be confusing for people, but hopefully it won't be. So you see, obviously, this f inverse, okay, I wrote it a little bit different than they did, but these are the exact same thing. So you're always going to have that a value given to you in the problem. So this says that f inverse of a, the derivative of that, will be 1 over the derivative of the original function at some value b, where f of b equals a. Now, so that means you're trying to find in your original function what value, so the a becomes, let's say in this answer would be 9, so you'd have 9 right there, and then you would solve, you could replace x with b, or you don't have to actually replace it if you don't want to, but I usually do, just for the fun of it. And then you solve and figure out what that value is. Now, it's possible, you might think, could this end up being, a complicated equation or anything like that? Well, yes and no. It could be complicated, but every problem we do, whether it's on an exam or quiz or in my notes here, I'm going to make sure that b is some sort of integer value. In other words, you can kind of get it. That means you can sort of get it by trial and error. You don't have to do some sort of calculator. Like you can pick a value that you think is going to be close and then work your way from there, up or down, positive or negative. And or you can actually let the calculator solve it if you want to, like graph it and find the intercept. But that's too much trouble. I don't think you'll need to do that. So we're going to take this problem we just had there, f of x equals x cubed plus x minus 1, and we're going to find f inverse derivative at 9, meaning we're accepting the fact that we're not going to be able to find the actual inverse function in order to take its derivative. So, and then I mentioned here, it'll be an integer or trig function where it will be a value on the unit circle, not just some random 1.2 radians. It'll be like a pi, pi over 3 or pi over 6 or something like that. Now we're going to need the derivative of our function, which that does not affect, usually I do this part first and then worry about this derivative, but you can kind of however you want to do it. So I just wrote the derivative there, so that's easy enough. So if f of x equals x cubed plus x minus 1, and then the derivative would be 3x squared plus 1. So we'll just hold on to that for a minute. We're going to need that, but not what we're going to do over here. So basically, I'm taking this equation right here and setting it equal to 9. Now, like I said, if you leave it as x, that's technically okay, but I'm going to use b just to sort of make it match the way the formula looks. But yes, all I'm doing is putting b in for this x and that x. So you have 9. Of course, I kind of wrote it the other way around, and it doesn't really matter, obviously. An equation doesn't matter which is on the left or which is on the right. But 9 equals b cubed plus b minus 1. Well, like I said, this is not going to be a complicated equation, meaning that you have to do some fancy stuff to it. Is go with trial and error. For example, I started with 1, but let's say you figure it's got to be positive. So sometimes you'll see whether it's going to be positive or whether it'll be negative. But if I put 0 in there for b, 0 plus 0 minus 1 gives me negative 1. That's not right. So I came over here and put in 1 cubed. I used 1. I tried 1. 1 cubed plus 1 minus 1. That gave me 1. That's not right. Then I tried 2. 2 cubed plus 2 minus 1 equaled 9. Bingo. That means b is 2. So you just can do it by trial and error. You're not going to have to solve this algebraically. You could actually put it in the calculator and put it in a chart, a table if you wanted to, and plug in values. You could go clear all this out. But that b is not designed to be complicated to find. That's not the idea. We don't want it to be complicated. So if I go x cubed plus x minus 1, and then go to table. Well, those are some values I had before there. I'll just delete those. But yeah, you don't always have to start with positive. I'll put a couple negatives in there just to show you. Negative 2. That didn't give me 9. Negative 1. Nope. 0. Nope. 1. No. 2. Bingo. There it is. There's your 9. So you can do it that way if you want to too. That's fine. But the b is definitely 2. Therefore, using the formula, the derivative of the inverse at 9 will be 1 over the derivative of the regular function at b, which is 2 that we found here. Now, yes, it is possible for b to equal a. That's possible. It could work out that way. So I don't want you to think it had to be a different. Like if you did it properly and you got the same number and for b as a and you were worried because of that, there'd be no need to worry. So it's literally 1 over f prime of 2. So it's really that easy. Once you get the b, it's easy. And then we already did the derivative. I could have waited, but there it is. So you put 2 in there. 3 times 2 squared plus 1 is 13. So it's 1 over 13. Now, since I could not graph the inverse function here like I did in the other problem, I just kind of drew a rough sketch, and a quite terrible one at that, actually. But well, I'm not going to try to draw it again, but I was trying to reflect it across the line, y equals x. But anyway, so it's a flat slope, 1 over 13 when you get out here to 9, versus the other one pretty steep. So, all right, that's a terrible looking graph, but that's okay. We didn't need the graph to get it. All right, here's another function. Assume it's 1 to 1, it will be. We want to find the derivative of the inverse at 11. Negative 11, excuse me. Negative 11. So we are going to need the derivative of this original function. So whether you do it now or later, doesn't matter. It doesn't have to be done first. Because to find b, you don't need the derivative. So there's a derivative. I just left the 1 over 27 there as a multiple and then took those two derivatives, which would be 5x to the fourth plus 6x, x squared. Oh, that's wrong, isn't it? Fortunately, I calculated it correctly in the next part there, but oh, all right. So that should have had a 2 there, shouldn't it? But you see, I corrected it. And we get a right parentheses in there, and then we're on our way. Good enough. So we have to find that f of b equals a business. So you come over here, and you can, like I said, use the calculator if you want to. But so you're setting this function here, whether or not you actually put a b in there. You don't have to. You can leave it as x. But I want to know what value would I plug in for x that's going to give me negative 11. And I'm guaranteeing you for these polynomial functions that it will be an integer value. So this is not some sort of complicated algebra exercise. So I'll just go ahead and come over here real quick and do this as 1 divided by 27 times x to the fifth better delete that, plus 2x cubed so there we go. So I can go back to my y equals, and I'm trying to get to negative 11. I go back to my table. Oh, trying to get out of that. X 2x cubed. So second, quit out of that mess. Now I go back to my, now I'll go table. And so those aren't right. Anyway, I'm not going to retype all these, but I'll just put in, so I'll put in negative 3, and then there it is. Negative 3 produces the negative 11 that we want. So that's it. That means your b value, so your b that you need to solve for is negative 11. I'm sorry, negative 3, excuse me. Because I say I worked all, okay, I kind of got rid of the fraction. So I could have treated this as, but obviously you see I put it in the calculator with the fraction. So, but anyway, like I said, negative 3 is the key value we need there. So therefore, the derivative of the inverse function at negative 11 equals 1 over the derivative of the original function, negative 3, which then I put negative 3 into the derivative. From we took the derivative, plug in, and I have positive 3 there, which is a mistake, but fortunately they're both squared, fourth and squared, so it's correct. But it ends up being 17. I'm just going to kind of squeeze a little negative symbol in there, like so. All right, that'll get the job done. So it's -3. And there we go. So it's 17. So therefore, the derivative of your inverse is 1 over 17. So now we have cosine of 2x on the interval from 0 to pi over 2. Because with your trig functions, you have to be careful. No trig function technically has an inverse. They would all fail the horizontal line test unless you just take certain sections out of the graph, part of it, to make it be one-to-one. As you recall, I did earlier, I showed that parabola graph and said, oh, what if I just took the right half of the parabola? That's what you have to do here. So you could not let this, you have to constrain the values to where it remains one-to-one. And 0 to pi over 2 is certainly good enough. So I want to find f inverse derivative at the square root of 2 over 2. So I've got to find the b value, or cosine of 2 times b is square root of 2 over 2 in this interval. Now what I did, instead of I didn't worry about the 2 till I came over here. But just think about it this way. Think about, let's just get the angle that we're looking for to be square root of 2 over 2. Well, the cosine of pi over 4 is the square root of 2 over 2. But since we have a 2 right here, that doesn't mean our b is going to be pi over 4. It means 2 times b would be pi over 4. Therefore, b would have to be pi over 8. See, if b is pi over 8, that gets me, and then 2 times pi over 8 makes that pi over 4. So now we know our value b is pi over 8. So now let's go up here and look at the derivative. Don't forget the chain rule. So the derivative of cosine of 2x is -2 sine of 2x, because we have to take the derivative of 2x. And then once we've done that, let's put the pi over 8 in there. So we have -2 sine of 2 times pi over 8, -2 sine of pi over 4. So it's -2 times the square root of 2 equals negative square root of 2. But that's not the answer, because the formula for the inverse, remember, is, I could bring that back in there, couldn't I? It's 1 over that. One over that. So we have -1 over square root of 2. I wouldn't care personally if, rationalize the denominator, but, like anything, if you're checking answers, they probably would have the answer with it rationalized. If I was giving a handwritten exam, I would not have a problem at all with it being left like that. But I just rewrote it. If you took top and bottom, multiplied the square root of 2 over 2. Well, this one might look a little scary. It's not that bad, because the derivative tidies up pretty nicely. So we're basically trying to find the derivative. See, they have to give you the a. They either can write it like f inverse a of 3 prime, or they can write this and say find the derivative of the inverse. But they've got to tell you what that a is. Our job is to find b, but they have to give you an a. All right, so I'll skip the quotient rule part here. I think we should have done enough of these by now where it shouldn't be too bad. Bottom derivative of the top minus top times the derivative of the bottom over the bottom squared. That numerator cleans up real nice. Just makes it -8 on top. So I have to set this original function, whether or not you change it to b or not, it's up to you, but I did. I changed it to b plus 6 over b minus 2 equals 3. Now this one, I talked about you can do it by trial and error, which is still true, but this one actually is easy enough that you can solve algebraically. So you can do it one of 2 ways. You can do it by trial and error, or you can do it like I did here algebraically, because it wasn't that bad. So I multiplied both sides by b minus 2 to get out of fractional form. So I have b plus 6 equals 3b minus 6. 2b equals 12, so b equals 6. And therefore, f inverse prime of 3 will be 1 over f prime of 6 that we just found. And then there's our derivative right there. So you see I put the 6 in for the x. So it's 1 over negative 8 over 6 minus 2 squared. So it's 1 over negative 8 over 16, which is negative 1/2. So that flips over and becomes negative 2. So your tangent slope of the inverse of that graph would be negative 2. It's actually interesting because it takes a little algebra, but you can get you can find the inverse for that function algebraically. But what I would probably assume, as far as you should assume for testing purposes, I'm pretty sure I would give you a problem that's you could not find the inverse function, meaning you have to do it by this technique, because I want you to use that, this formula right here. I want you to do it that way. So to force you to do it that way, I can just put a function that's not algebraically solvable to find the inverse. All right, so we're going to conclude with one more example, a trig one. Tan of x between negative pi over 4 and pi over 4. So we need to know the derivative of sec squared. And we're looking at, there's our a, square root of 3 over 3. So I need to set our f of x, tan, and make a tan of b, set it equal to the a right here. So in other words, f of b equals a. F of b equals a. So I'm looking for where tan of b equals square root of 3 over 3. Now you can play around with this because, as I mentioned, it's got to be something on the unit circle. So it doesn't require, you can just try some values till it works. We know we have to be between, now be careful, this says 7 pi over 4, but remember 7 pi over 4 is the same as negative pi over 4 if you're going in the negative direction. So we're going from here to here, but we just don't call it 7 pi over 4. So but that means this is negative pi over 4, the next angle is negative pi over 6, then 0. So you don't have much to try here, really. It has to kind of be something. So yeah, it wouldn't be hard to figure this out. You have limited options here, but if you try pi over 6 and see what, just check tangent of pi over 6, you'll end up with that value. So what I did is I plugged it in and saw that it matched. So it checks, therefore your b had to be pi over 6. And so it's pi over 6. So that means the derivative of the inverse of the square root of 3 over 3 would be 1 over the derivative of the original function, which is sec squared. So it's sec squared of the b that we found, which is pi over 6. And so 1 over sec squared then is the same thing as cosine squared. So it's cosine squared of pi over 6. So it's the square root of 3 over 2 squared, which turns into 3/4. So that would be the derivative of the inverse function at the square root of 3 over 3. And that concludes the video for inverse functions and their derivatives.